Robert I also was one of us at Fishworks at Sun, and has joined us here at Joyent. So Robert and I, along with Max Barting, did the KVM work. Robert's threshold for pain is outrageously high, which has been a terrific asset. I'm extremely excited about the work that he's going to present right now. We're going to go into some technical detail here. I noticed that the recruiters have left, so the recruiters took their first opportunity to hit the exits, like the hitting the recruiter panic button. So I mean, this is going to take us into the real details here. This is a tremendous leap forward for Illumos. You're going to see this in all the distributions effectively. So Robert, take it away with per-thread caching from libumem.
Woo! Yeah!
Hi everyone, I'm Robert Mustacchi, and I'm here to talk about adding per-thread caching to libumem. So let's start off. What is actually libumem? So it's basically a library that you can use as a drop-in replacement for the malloc and free functions. These are the functions that every C programmer ends up using to basically do dynamic memory allocation. So they'll go in, they'll call malloc with some size, they'll go back later, and hopefully they'll call free of that same pointer. You might know them really as these are the functions that people call to increase the V size in RSS in your PS output. Hopefully the people actually go and it lowers at some point in time. But when it doesn't, libumem also provides the tools that we have to go and figure out why you've basically been leaking memory and where that memory is. So why does the performance of the memory allocator actually matter? So I mean, who actually calls malloc? I mean, come on, we're not all writing C programs, but at the end of the day, actually a lot of stuff does go and call malloc. So if you use any C++ and use new or any of the other fancy ways C++ has to create abominations of objects, basically you're going to end up calling malloc under the hood. Thankfully, we actually understand that, so that's good. And all of the garbage collected language or scripting languages that you end up using, they actually all end up calling malloc in one form or another. So I've just gone through and basically ran a few different programs. So the kstat program prints all of the kernel statistics. So there's a lot of statistics in the kernel that we have. So everything from basically what are your CPU caps to how much memory is used to how many packets have been transmitted on these various networking devices. And so those are all getting dumped. So that's a Perl script. And that Perl script, 670,000 mallocs. And that runs for a long time.
Wow.
That's lots of mallocs. So now, let's do something simpler. So there's Mercurial, which is a source control piece of source control software. You just run HG, which just is printing out the usage message. So it's not actually doing anything particularly special, nothing fancy. Well, that's 3,800 mallocs. So then also here's this a Node.js application. So you're like, great, I'm using V8. V8's doing all this nice garbage collection for me, just like the Java hotspot engine would. It's like, no mallocs there. No, you're not quite so lucky. So they're just doing a VM-ADM list, which is just listing out all the VMs. You're doing 2,700 mallocs. So not all of these are the most time-sensitive applications. I mean, obviously you want your listing of all the VMs to return pretty snappily, but a few microseconds there doesn't make a difference. But if this is your production server, those microseconds basically translate into latency. If this is basically serving your Apache website or just you have some web server, those could actually end up being the difference between customers loading your web page and it being snappy or not. If you're doing, for example, online retail, pretty much there's studies basically say consistently, the more latency you have, I mean, we've all been pretty lazy with, okay, page isn't loading for 5 seconds, like close the tab, move on, and just kind of forget about it. So just to kind of, here's another example, basically where this comes into play. So here we had a flame graph. So basically what this is something that Brendan Gregg did to help us visualize profile data. So we went and we profiled an application, and basically we have the stack frames kind of all lining up here. So what we care about now is whatever is here up on the top. Because those top segments, those end up defining and describing where our program is actually spending its time. So we've used dtrace to gather this data. In this case, this was a Node.js-based application. So we have both the JavaScript stack frames, which is thanks to Dave Pacheco's work, and we also have the just the C and C++ forms. Fortunately, you can just make out the mangled C++ names and despair. But so basically, all of these little peaks that you see here with these twin towers over the place, those in this case are all mallocs. Those are all times that we're spending in libumem doing malloc, calling a few different function calls, doing some mutex locks, and that's all time we're spending. That's all time that the customer application is spending doing memory allocations. And in this case, there's quite a lot of this. So to understand what we're doing, we have to understand a little bit of how malloc works. So we're going to actually go step back in time a little bit that probably most of us all remember to 1988. So the version of malloc in libc still has the AT&T copyrights from 1988. And so this is pretty much one of the simplest but performant malloc implementations there are. So in here, only one thread in the given process can be trying to get memory at a time. If another one comes along, it's going to be stopped and block until it's finished. Then we basically array all of the different chunks of memory we have in a traditional, just simple binary tree. We're going to end up searching that binary tree to see if we can find something that matches our size. If we find it, great. We remove it from the tree, we return the pointer back to the application, we unlock, and we're done. If we don't find it, we go to the operating system, and we end up asking the operating system for more memory. This is sometimes where you end up seeing us, basically, that's where PS starts to bump itself up. So this is good, but not that good. So anyone here actually run Solaris 2.4? Great, okay, so those of you who did, maybe know, or hopefully just benefited from the slab allocator. So that's something that Jeff Bonwick went and introduced, and since he introduced it, let's see, Linux, I want to say HPUX, several of the BSDs, maybe even AX. Basically, everyone has gone and taken the slab allocator and brought it to their operating system. So the key insight to the slab allocator is just that most of the time we're accessing certain sized objects. So there's a lot of good examples of this. On disk, each file is represented by something called an inode. So that's just kind of one fixed size structure that you end up allocating a lot of. If you think about every time you send a packet, in Lumos, there's something called a message buffer, so an mbuff. That's a fixed size struct that has a specific kind of signature and basically specific size. The internal ARC data, so the ZFS ARC, and its metadata end up actually having several different just kind of commonly sized structures. So rather than going back and doing one-off allocations from the main memory, what we're instead going to do is basically allocate a bunch of these. So we're going to basically say, I'm going to allocate 50 or 100 of them and put them in a slab. So when I'm going to come to my allocation, I've already actually allocated these. I'm just going to just pick one off the top and just give it to you. And if I run out of this slab, then and only then I'm going to go and allocate a new large chunk of memory and divide them up into these objects. So the main benefits here are you could end up actually doing a lot faster memory allocations. You also, the big one is that you end up reducing your lock contention. So in the previous kind of original implementation, you basically had one lock. So only one thread could be grabbing stuff at a given time. Now we've changed that granularity. So now each cache has its own lock. So it's a much more fine-grained system, so you can get much better throughput. In addition, with a lot of this work, there's actually a lot of work being done to basically make it so you can understand and basically help debug memory. So, a lot of times people cite that they hit memory bugs and that they would just kind of wish they could have a better understanding of why it went wrong, and kind of just, it's a common C programmer's nightmare. So the idea here is that basically you can go in and knowingly annotate certain regions of memory with just basically ways that way, oh, hey, I just told you to I just gave you back this memory and I just used it again. And so that way we can go in and detect that and understand what's happened and abort the program so that way it can be understood. So this was good, but not good enough. So in Solaris 2.5, did more people, anyone who didn't run 2.4 run 2.5? So 2.5, good. So the whole idea here was magazines. So if you're familiar with the idea of a magazine from an automatic weapon, this is actually the exact same idea. So for rifle, you think the old kind of 22 bolt action rifle, one shot, take out the bullet, put a new one in, close it, shoot again. Great, fine, but pretty slow. Takes a lot of time in between reloading. So instead, the whole idea of you introduce the magazine, you can do a lot of shots before you end up having to reload. So we actually basically want to do the same thing, but on a per CPU basis. So once you have a lot of CPUs, you have a lot of things that are going to be wanting to say, allocating packets. I mean, who here runs 10 gig networks? So you're sending a lot of packets across those networks, even a 1 gig network. You have multiple CPUs trying to do that, multiple programs trying to send packets out. Those are all going to try and go into the same cache. And that's going to be a pretty huge barrier. So instead, we're going to give each cache a per CPU magazine. So when you come in, you're going to go to a specific, whatever CPU you're running on, you're going to go and allocate from its magazine. When it runs out, it's going to go back to the underlying kind of core stuff and just allocate more memory and just create a new magazine to reload. And there's one actually kind of really neat feature here, in that when we go back to the kind of core to reload the magazines, we actually have a built-in way of detecting if there's a lot of we're going through a lot of objects. So if there's a lot of contention on the kind of global cache there, then we're actually going to increase the size of the magazine, so we reduce, so basically we're increasing how long we have between reloads. In addition to this, you basically had a kind of a fun things just to basically make the CPU and kind of memory faster. So you can basically play tricks with your hardware caches and to basically make sure that things are aligned properly to load faster, but also that if you use the same kind of address, if you think of it, most of the time you get stuff kind of say in page sizes. So OX 1000, OX 2000, OX 3000. If you keep everything at 0, it's some of those lower bits in the CPU, and if they are all the same, those end up actually kind of going to the exact same locations in the hardware caches, and thus actually can end up hurting your performance quite a lot. So nice thing is you don't have to think about this, and I don't have to think about this. Thankfully, Jeff thought about this for us. And so there's notions of cache coloring, so we don't have to worry about basically, are we taking the most advantage of the hardware's underlying resources? Are we kicking ourselves out of it? I mean, even getting the CPUs to tell us that this is happening is hard enough with observability, so it's a good thing we don't have to worry about it. So this is pretty good, but it was all for the kernel. So in 2001, Jonathan Adams and Jeff Bonwick deployed libumem. And you first saw that probably in Solaris 9 Update 3, is kind of what our thoughts were on that. Who here ran S9? More? Okay, that's...
Who here still runs S9?
Yeah, I guess who's here still runs S9? That's good.
He was a good one. 2 or 3. It's good.
It is a good year.
It was a good one.
Still runs.
Not as good as 2.6.
Yeah. So the whole idea here is we're going to take the kernel allocator and just bring it to userland. So that way userland applications can actually have all the same benefits that we've been using inside the kernel for years. Nice thing here is that now, basically we're talking about all those memory leaks that you end up having. You can actually just turn on debugging, just take your standard core file, and just use MDB, which is the Solaris modular debugger, which Illumos properly is kind of driving forward, and then just use : find leaks on it, and it will actually just basically show you where all your memory leaks are. Just say, hey, we found all these unallocated buffers, here's where they're coming from, and basically you can use that to go figure it out. And they'll even give you the full stack backtrace. So they say, you can basically say, hey idiot, like, you did this here, and you forgot it over there, and it doesn't lie. The other neat thing here is that, so normally when you call malloc, we had that whole binary tree that we're going through, and we're trying to figure out kind of where the best place is, and that's kind of okay, but not great. So instead, we're actually going to use fixed-sized caches. So there will be a 128-byte cache in 8, 16, 24, 32, kind of increments itself, kind of increasing its size as the memory amount gets bigger to about 128K. So when you do a 100-byte alloc, you call malloc of 100, that's going to actually go to the 128-byte cache, go to your per CPU magazine, and take that back. So the whole point here is it increases your ability to kind of just have high throughput, and basically we're reducing the contention as much as possible on those locks. To go and use libumem, you can actually use it today on any Illumos or even older Solaris-based system that you have. Assuming your application's been already built, just use LD preload and go from there. If you're building it and you want to always use it, you can just force the program to link against libumem in the compilation phase. But if you're just going from your package manager and your program isn't linked with libumem and you just want to give it a shot and see how it is, you can just use LD preload and go from there. So this is all good. Why are we doing any work here? I mean, unfortunately, libumem does start to break down a little bit. So in the kernel, it's actually just 4 x86 instructions to grab a mutex. That's it. Just 4 instructions, assuming you get the mutex. If not, you're going to spend a lot more time. But in userland, unfortunately, it's a lot harder. The kernel is basically blessed and cursed with being able to use kind of secret knowledge. So the kernel knows when it's going to be preempted. The kernel basically can say, hey, no. You're actually not going to kick this guy off CPU because I control who runs on CPU. In userland, you don't get that luck. You can't say, you can beg to the kernel to like let me run for a little bit longer, but when the kernel decides to take you off CPU, you're at its mercy until it puts you back on CPU. So for example, in the kernel, there are even places where we actually check to see if you're in the region of mutex enter, and so we actually won't preempt you. So because this lock is a little bit more expensive, and remember, every allocation forces us to grab a lock. Now, where does this get bad? Well, some applications are kind of bad actors. Yeah, they're actually doing on the order of tens to hundreds of thousands of allocations per second. They're in small, tight loops. They do a small malloc, use it briefly, and free it. A lot of these times are actually things where the application itself could be improved. Unfortunately, we don't always have that luxury. We can't just go say, hey, talk to your ISV and go tell them to go fix this. It's like, yeah, right, they're not going to, it just doesn't work that way. So we have to go address this, especially when these similar software works faster on other systems. So a customer says, hey, I used to run this program over here. It's a lot faster. Like, why is it slower here? And unfortunately, this is sometimes the cause. So helping address this helps us keep customers. So an important thing here is to make sure we're focusing on the right problem. As we said, we had to grab a lock. So your initial thing might be to say, you're using the vile mutex. Mutexes are always known to be evil. You should always get rid of them. We can use atomic operations to do wait-free and lock-free synchronization. That would be great. Unfortunately, that's actually not the problem here. The problem isn't that we're trying to do any kind of, we're actually trying to use locks. The problem is that we're actually trying to do any kind of synchronization at all. After all, it's much easier if we don't have to talk to someone and communicate, and we can just do whatever we want. Things go a lot faster. We don't have to worry about waiting for someone else. So the solution here is to add the notion of a per-thread cache. So instead of going to the per CPU, basically figuring out which magazine corresponds to the CPU, having to grab a lock, make sure no one else is using it, I can instead just talk to myself. And my thread knows everything that it has. Don't have to worry about anyone else coming along. Brian and Bill don't have to worry about sharing and sharing the backpack. I mean, only one person can use that at a time. So, but if both of them had a backpack, then in this case they both do that.
I think we've taken that about as far as I can go.
So to actually go about this, we have to do a little bit of careful planning. So when you actually go and allocate, you call malloc, you give it some size. I was like, sure, you got that size. Actually, malloc lies to you. It doesn't tell you the truth. Because if you know, when you go and call free, you don't have to pass in that size anymore. So that size has to get stored somewhere by someone. So what malloc actually does, and it does this in both like glibc, so this is across multiple implementations, it's kind of a time-honored and classic tradition, is that it's going to actually store a little bit of extra data either before or at the end of the buffer you requested. And in that, it's basically going to store, here's the size. So it's like, you allocated 32 bytes. Well, here's how I actually know where that is. Now, this is a tax that's on the memory allocator system. So if we're going to improve this on a per-thread nature, we shouldn't change that. We shouldn't increase that, because that means now every allocation in the system is going to end up suffering that cost. So if we're going to add memory overhead to do per-thread caching, that means someone's going to have to pay the cost of that memory, which is your DRAM, and we like our DRAM. We don't want to kind of see it wasted. The other challenge here is that we don't want to increase the fragmentation that's going on. So if you think about it, when you go and do a malloc with libumem, so you do that 100-byte malloc, which goes to this 128-byte size cache. You actually end up allocating 128 bytes. The alternative would have been to basically say, okay, I took this 128 bytes, split into 100 bytes and 28 bytes. And I really hope someone else comes along who needs 28 bytes, but if not, I'm kind of out of luck. So instead, you basically we give you that as a little bit of overhead for using that cache. And when you come in for doing 28-byte allocation, you instead go to the 32-byte cache. So basically, you're going to different size caches for a reason. So in this case, we want to leverage the size of these caches. So when you're putting it in your thread, and you allocate 100 bytes, and that allocation is good for 128 bytes, we better well be able to use it for up to 128 bytes again. Like, let's not cap it at 100, because then we're just wasting those 28 bytes. So this kind of constrains our implementation because we don't want to basically waste additional memory in terms of fragmentation. Unfortunately, or fortunately, depending on your point of view, you can actually tune the size of the caches that exist. So if you basically know your applications going off and doing lots of 10-byte allocs or doing lots of 4K allocs or 4005-byte allocs, you can create a specifically sized cache for that at runtime as part of starting up your program. So when we compile libumem, the set of cache sizes that exist are not known. We have here's a base set that you'll use if you don't tell us anything else. But we can't basically say, never tell us anything else. We can't basically strip out something that we've basically told everyone exists. So we're going to basically have to do some dynamic generation here. So libc, the C library, basically ensures that each thread has something called an uber data. The uber data basically consists of all this magical information that you never have access to, but the operating system needs, so basically you get the right data. So when a thread has an error, that error and what that value is stored off in the thread's uber data, so that way, just by having multiple threads sitting around, you don't get lost and confused. We basically then have 16 slots. So we basically we can get 16 per thread caches here. After we determine the final set of cache sizes, we basically create a direct mapping between the first 16 caches and these 16 slots. So the first slot corresponds to the first cache, second cache, and so on. That way, when a thread comes in and first is going to do malloc, it's actually going to go check if the size is within that range of the first 16 caches, it'll go check that cache to see if something's available. If it is, it just grabs it and runs. Doesn't have to talk to anyone else, doesn't have to worry about synchronizing with anyone else. If on the flip side, when it's coming to free, it basically says, hey, how much data have I stored? If I haven't crossed a certain threshold, great, I'll just store it there. So each of these slots is just basically a simple linked list, and you just toss stuff on there and go. So let's actually just kind of describe a lot of history and theory. So let's just see, what does this actually mean for us? What does this actually translate into? So we've gone here and we've basically done a simple GNU plot graph. We basically did a couple million allocations, just a tight, malloc, and free loop. So basically, what's the simplest possible kind of thing you could do? Just malloc it and free it, don't add any additional overhead. So we basically put up 4 different things. Here's what libumem used to be the worst. So we had a lot of room to go. It was actually worse than libc. This is a single threaded allocation. Once you do a lot more than one thread, libc kind of just takes. For comparison, we had an identically spec'd machine that was running Ubuntu. I don't remember what version, so this is basically just comparing us to eglibc, which is actually pretty good, I gotta say. Like, they've done a lot of good work in there, and they've done a lot of work to make it really fast and really performant in a lot of cases. And then here's us. So basically, we're coming in, and we've basically, because of how we've done this and adding this per thread cache, we've really tightened down and limited this speed. So that's right, that's the smallest cache. So how does this go across all the caches? So here we just have a simple case of, again, looking at the per thread caching. Basically, here we did 512 million mallocs in a row. Just malloc free, malloc free, malloc free, malloc free. Basically, that's basically the most pathological case an application could do against the memory allocator. Basically, what's the worst you can do? Let's see how we're actually doing at it. And so in this case, again, glibc here is just really just for our own sanity check. Basically say, if this solution wasn't actually faster, or where what we've gone and done is basically hand-generated a bunch of assembly, then we have some problems. So basically, this is basically a good proof of concept. It's like showing us that, yes, we were actually doing the right thing, and yes, we are actually getting the performance improvements that we're expecting. And so you see that in this case, it kind of, because of the way the assembly is written, it ends up scaling a little bit linearly, approximately with which cache and which slot you're in. And if for some reason that linear, you want to make that better, I mean, we can talk and let's do it. So let's go back to actually to the original flame graph that we looked at. So there used to be all these high towers and spikes that we had that corresponded to all the memory allocations. So we've actually gone through and eliminated most of those, which is great. This means that now, if it's too slow, we actually need to go back, look at this graph, and figure out where else we have these kind of large kind of chunks of time. So like, whatever that is, we're definitely spending a lot of time there. So like, who knows whether or not that stuff is necessarily optimizable or not, but the whole point is that what we've done is we basically took a look at the original profile of the application. We saw we were spending the majority of our time. We kind of target the first, kind of the biggest case, and now that we've solved that, we can go back, look at it again, kind of figure out what the next thing to go tackle is. So in this case, we basically see that it helped the customers out a lot. It helped us out, kind of helps everyone across the board, so that was good. So as alluded to, here's actually some of what's going on under the hood. It's a little hard to make out, but basically what you have here are a series of just numbers. These numbers correspond to x86 assembly. So what we have to do here is, because these cache sizes aren't known until runtime, is that we have to basically dynamically generate the assembly, the machine code that's going to run. So we basically have tables of machine code that basically you plug in all the appropriate offsets in, and those get jammed into your address space. So when you call malloc, you're not running the nice little mallocs that the C compiler did for you, and yeah, you turn on all of your optimizations, and that's great, but it actually isn't that great. Like, the optimizations don't solve your lock problem. So instead, you basically have to kind of hand roll a bunch of stuff, and that's just kind of
Making sweet love to John von Neumann.
So there's a bit of tuning and introspection you can do. So the default cache size for each thread is 1 megabyte. You can tune that up or down, as the case may be. So ask yourself, how do I even know if this is working for me? Like, should I increase it? Should I decrease it? So Brian went and added and enhanced the UMA stat command as part of MDB. And basically, from here, you can go and look at and understand how effective is the per-thread caching. What am I caching in here? Do I have a lot of spare memory? Am I using too much memory? So basically, we have the total percent in the cache that each thread is doing, and then we have the basically, what percent of that is within which size caches. So here we see it's basically in the 160 byte cache, is where 93% of it is, and we're only using 20% of our allocated space in that cache.
So how does this deal with a pathological case of like in-memory queues where one thread is doing all the mallocing and another thread is doing all the frame?
So unfortunately, that's basically not going to end up helping it. In this case, you're going to hit your cap, and you're just going to end up going back to malloc first. So it doesn't solve that problem of basically passing it across multiple threads.
If you set it to 0, it'll completely disable itself. So if you do have a pathological application, it can set its own unit option to set its cache size to 0. Correct.
So there's a bunch of references, which if you're curious about the actual papers where a bunch of this stuff came in, the debugging, that stuff, you can read up on it, and the slides will put them up online. So, any questions or other stuff?